Very good evening to everyone. I'm Nikita from SSCRD and Genex Space. I welcome you all to the Space Talk. It's been a long time, I know, from doing this program, exactly a year to be precise. But yes, here we go. We are with all of you with another amazing space talk. And World Space Week is the best occasion I feel to come back. So I wish you each and everyone a very happy World Space Week. Today being the first day, we have arranged this guest talk, especially on a very interesting topic. Now, to talk a little bit about us and then World Space Week and then to the topic, we are known as SSCRD and Genex Space, where the main goal is to create awareness about space science, um, prepare everyone for this amazing work that's happening in India and globally in the space domain, and to prepare those future workforce for the entire world. So that's the main objective. And these talks with experts are for those who want to learn, who do not have access to the experts and the information that you can easily do not access. These talks from the experts give those information to everyone, and I again welcome all of you for this guest talk during the special occasion of World Space Week. Let's say the topic for the day is laser satellite communication. And in fact, the theme for this World Space Week is living in space. So I was thinking about living in space, if it has to happen. I think one of the very important point over there is the communication. We need to start talking, we need to start communicating with everyone who is there in space. And I feel we need to look at what are the next best technologies for communication. And I found laser satellite communication. And here we have Tushar Goyal, my friend, my let's say friend from ISU network. I welcome you, Tushar, for this guest talk, which we have, and an amazing topic that you have chosen. I welcome you.
Thank you so much, Nikita. Pleasure to be here and pleasure to be talking to everybody who's interested in this topic. I picked this topic specifically because it's one of the future things that are upcoming and will be the future of communications. So I thought it'd be good to talk a bit about laser satellite communication.
Amazing. Thank you so much. So let me quickly introduce Tushar to all of you. So Tushar Goyal is currently serving as the head of business development, space products at AAC Clyde Space, where he leads commercial strategy and growth for advanced spacecraft subsystems. With a foundation in aerospace engineering and a deep interest in astronomy, Tushar holds an M.Sc in space studies, which guides his technical understanding of the space domain. Earlier in his career, he has engaged in roles that blend engineering, science communication, and business, making him uniquely positioned to translate this cutting edge space technologies into viable market offerings. He's also active in the space community, often speaking on topics like laser satellite communication, innovation in small satellite systems. Tushar's multiple disciplinary background, commercial acumen, and technical insights make him a strong bridge between science, engineering, and business in this growing space industry. Tushar, again, I welcome you for the space talk with SSCRD and Genex Space. Um, I request all the viewers who are here to kindly listen and do put your questions in case if you have any on the chat. Um, so we're gonna let Tushar to talk about this technology, what he's working on, his company is working on, and at the later part we're going to have this very interesting, very nice Q&A session. I have few questions from my end, but if you have any questions that you want to ask Tushar, you're free to put it in the chat, and we will pick up some interesting questions from the chat and ask Tushar on them. And if you have not subscribed to our channel yet, I request you to subscribe. And Tushar, if you're ready, I will allow you to take over the screen.
Thank you so much. And thank you so much for the kind introduction. I'll try to do my best. Yes.
Awesome.
Is my screen visible? Okay, perfect. I will quickly introduce you guys to AAC Clyde Space, the company that I work for, and then we'll dive directly into the topic. So, AAC Clyde Space, we're a new space company. We have been founded in 2005. We're over 200 people, and our major operations are in Europe, North America, and Africa. We do three main things: space products. We build anything and everything you need to make a satellite. We do space missions, so we manufacture a full satellite and can deliver that in orbit for our customers. And space data as a service, we deliver different kinds of data from space to basically aid in agriculture, ship tracking, various applications throughout the globe. Moving ahead, we can produce over 30 satellites a year, and we make many products every year. As I mentioned, we're a bit all over the place. Our headquarters is in Sweden. We're in the UK. We are in the Netherlands. That's where I'm based at the moment. We're in South Africa. We're in the US, and we have another office in Sweden. And these are all different divisions where we perform different. We have different specialities in all of these different divisions, basically. As I mentioned, we mostly do the small sat market, which is up to 500 kilograms. We have some stuff that we do more. Our space products have been everywhere here on Earth. We have some stuff on the moon, and we have some stuff headed for Jupiter as well as we speak. Let's dive into the topic, which is laser satellite communication. And before laser satellite communication, it's first thing I want to talk about is why satellite communications or SATCOM in general. So, SATCOM, laser satellite communications, is a part of our everyday life. It's from television to the dishes that you see, which is changing these days. But you used to have dishes from which you would get Tata Sky, Dish TV, etc. All these were operated through satellites. Interconnectivity, internet connectivity wherever our terrestrial networks cannot reach. Why you have Wi-Fi on planes now, you have Wi-Fi on ships now. All of that is done through satellites. Navigation and GPS, like these days, I don't know if somebody can navigate without GPS if you're going to a new city or driving in a new place. So navigation and GPS is something that's like become part of our everyday life so much that we don't even see a life without it at the moment. Disaster response, anywhere where their terrestrial networks get destroyed because of a natural disaster, the only way to reach those places is through satellites. Then we have industrial applications. We have oil and gas industry. We have agriculture, transportation and logistics on your, food ordering app. You're tracking your food all the time. That is all made possible through satellites as well. Your finance, your banking services, all of that has been made through satellites. There is an increasing need for satellites in defense and security to make sure that we live in a secure environment and everything is fine. So, in short, SATCOM is not just a niche technology, it's really the backbone of modern connectivity. It touches every aspect of our life, from entertainment to emergency response. And we use satellite communication every day in our lives. without even realizing it at times that we have that power in our phones, in our hands, and we use it every day. It's super important part of our lives today. Now, here is an example that I wanted to show you guys. This is so we also track the weather through satellites, and we make predictions through that, so that we know how what kind of weather we can expect, what are the effects of climate change. This is one of the instruments that we have built, uh, and all of this information, this is the information that you're trying to get from space, and you're also communicate basically getting this information through satcom only. So satcom is a part of everything from predicting weather to, as we mentioned, entertainment earlier. Now, why lasers, and why did I choose the topic of laser satcom, and what? So traditional communications from satellite are done through radio frequency. We have seen there is a spectrum. I'm not sure if you've heard this term. It's a common term being used. The spectrum you have to license. So if you have the FM in your car, you choose the station 93.5 or 98.3 or something like that. So that is the frequency that's basically, in simple terms, that's allocated to that radio, so that you can listen to it. You tune into that number, and you can hear basically your songs or whatever news updates you're going. So that's how typical satellite communications have been taking place till now, with the help of radio frequencies. Now, there are few advantages of using lasers. Now, radio frequencies, you all have heard about data rates, speeds, megabits per second, gigabits per second. Radio is limited to these speeds. We cannot go much higher in terms of radio depending on different availabilities that we have. With lasers, we can go up to gigabytes per second, or up to 1000 gigabytes per second, which is terabytes per second. So this is something that gives lasers an edge and makes it future technology, because right now we live in the data age. All we want is fast internet. The faster internet we get, the better it is. We've all heard 5G, 6G, and all of these things are incorporating laser communications in them. The other is the spectrum availability. Now, for radio frequencies, the I told you that 98.3 is assigned to somebody. And basically it's they have the license to operate at that frequency. With lasers, we operate in different wavelengths. Wavelengths part of the electromagnetic spectrum. This can be infrared, this can be in the visible range, but mostly for communications, we use infrared. Now, you don't need to license the wavelength in which you are operating. But because there is no, if you are operating at the same frequency, you will have disturbance over the radio. You will not get a clear signal, because both two different things are trying to communicate through the same frequency. With lasers, that is not the case. You don't collide with each other, and you don't have to do licensing for lasers. So that's another advantage for lasers. Then we have something that's very important to space, which is size, weight, and power. So laser terminals, or laser communication terminals, they can be much smaller and lighter, and would need less power than traditional radio frequency systems. Radio frequency systems are mostly bulkier due to they need big antennas to cover a big area, and they have high power needs. And these are two things that we, don't have a lot of liberty in space about. Then there is the aspect of security. Lasers by technology are secure. Now, when you are broadcasting through RF, you might have seen this in a movie or somewhere, that somebody's trying to listen in, the police radio, or they're trying to listen in through a satellite signal by pointing their, mobile device. Basically, they have to track those signals. Now, that can happen with radio frequency, because the radio frequencies, they are extend in kilometers in width. Basically, when it is coming down from space to Earth, they expand across kilometers, and basically you can intercept it anywhere. if you know the right, codes, etc., to be able to intercept it. Some are very basic, you can just intercept them directly as well. With lasers, this is much more difficult. Uh, th- with lasers, it is a very targeted beam, and your beam will be only in a few hundred meters. So it's not, you can't easily jam it, or you can't easily listen in. So this is the aspect of security with lasers, that just because of these being different technologies and it using light, the beam is very much broader, and basically you're not able to track it and you're not able to listen in. And these are the four major you know uh, advantages of lasers over radio. And this is going to be the future of communication. Direct to device, 6G, all of these applications will be served through lasers in the future. Now, how does this actually work? Now here, this is, a basic, so on the left on the top, you can see this is our laser communications terminal. I'll talk about it a bit more. And at the bottom, you have the ground station. Basically, from the terminal, you're transmitting the signal to the ground, and this station, optical ground station, is basically collecting the signal. Now, how does this work? You have a big laser from the ground. Basically, I'll give you more details on the laser. So basically, there's a laser beacon on the ground, which it will fire to space. When this and the ground station knows when the satellite is coming above it, basically, and then it fires the laser. The terminal sees the laser, locks onto it, and it gets inside. Once this is locked, it will fire its own laser towards the ground station. When there is a lock on the ground station as well, I know there is a lot of moving parts in the middle. I'll explain them as we go further. Now you can see there is a data transfer happening finally. So these are secure systems. Unless they exchange the right information amongst each other, they will not start transmitting data. And that's how this works. Basically, you have to have a laser beacon on the ground that the satellite will see. It will lock onto it, and it will start transferring the data to the ground station once the keys are matched on both sides, basically. So it's secure, and it's much faster as well than traditional RF. Now, talking about the terminal that we have, basically, and then going a bit deeper into laser communications. The terminal that we have, we call it the CubeCat. It's the smallest, fastest ever proven in space. It's only 1 kilograms, and it's only 10 by 10 by 10 centimeters. So it's a small box. It has a laser inside it. It has many more systems to coordinate the laser, to get your data in. It has storage, and basically it is the smallest, fastest ever proven in space. It operates at 1 gigabit per second. Now, to give you a bit more specifications of these terminals, basically these are bidirectional, so you can send data up and you can send data down. Now, you can see the downlink is 1 gigabit per second, but the uplink, as you can see, is only 200 kilobits per second here. The main reason for that is the small aperture. Now, this thing is so small that the aperture you can see in front here, this aperture is very small. And it limits our ability. It's the same principle as a telescope, basically. There is a telescope inside this, and they work on light collecting power. And the bigger the size of your mirror or lens, the more light you can collect. So there are physical limitations. And that's one big reason that the uplink, as you can see, is only 200 kilobits per second. On the ground, we can have a big telescope as a receiver. And then we can collect a lot more light coming. And then we can have higher data rates. Now, here then we have the wavelengths that we operate on. It's 1545 nanometers. This is in the infrared region. Now, this is a safe. Basically, you might be thinking that if you're firing lasers up and down, could you burn something in the middle? Could you hurt a bird? or anything like that. So that's not the case. These are safe lasers. They operate in the infrared range, and they do not have enough power to harm anything or burn anything on their way. So these are safe to be operated from space, and they're safe to be operated from the ground. You don't need to get the airspace cleared out for these. But these are the wavelengths that we operate on. These are two different wavelengths. 1545 is when we are downlinking, and 1590 is when we are uplinking. And this is so that we can use one telescope to separate two wavelengths. Basically, we use a filter that allows us to differentiate between these two wavelengths. Now, every laser or everything, you will always have a range till which it can work. You can't go infinity. So this particular thing has been designed for up to 1000 kilometers, which is for low earth orbit, is what it is designed for. And we actually launched this terminal in 2023, and I'll show you some results of a bit later from an in-orbit demonstration as well. Let's deep dive a bit into inside the terminal. How were we able to fit everything in such a, or what are the main building blocks of this terminal, and what are the challenges here? Now, as you can see, the main five building blocks of this terminal: the structure. Now, the outside structure of the terminal, the silver thing that you saw, it's very important because if so, there could be vibrations from the satellite to the terminal, and if it is doing this, basically it can't do its work. So the structure is responsible for absorbing all those vibrations and basically allow the telescope inside to operate without those vibrations, damp free. And that's what the major thing for the structure is. It also basically has all the components together and make sure everything is inside and intact, because when you're launching on a rocket, there is a lot of vibrations, and this structure is again responsible for keeping everything in place. Otherwise, things might not work when you go to space. The fine pointing system, super important. As I said, laser beam goes very narrow, so you need to point at the place where the ground station is. You are 400, 500 kilometers above Earth, and you have to point at a place on the ground. So you need to have very precise pointing. You need to know exactly where your ground station is so that you can point the laser beam at the right place so that your data is transferred. Optomechanical assembly, which is basically a telescope. It's a combination of optics and mechanics to be able to do the telescope basic to be able to do the data transfer the laser to the ground and receive the laser from the ground. And then, most important is the laser and the detector itself. So the laser is there. It's a 300 milliwatt laser, and there is a detector. So the laser transmits the data. So everything gets encoded, sent to the laser transmitted down, and the detector basically records what is coming from the ground in it. Then you have control and data storage. Now, these are also super important. Now, when you are in space, when a satellite is in space and it's orbiting the Earth, it's going at 7.5 kilometers per second. So it's going super fast. And so the control basically, it predicts where the satellite will be next so that the laser can keep pointing in the right direction towards the ground station. So the data transfer can continue. Now, why is the data storage important? You want to get the data. So, for example, here you can send any kind of data. For example, it's images of the earth that you've taken. You were looking at a natural disaster, there is a wildfire somewhere, you've taken all these images, and now quickly you want to get them down. So, you would basically store them inside, and you would look for the right moment for a pass above a ground station, and as soon as you will let the payload, the camera, keep collecting more data while you have already have the data that you want to send out. So you would take that data into the system already, and as soon as you have a chance, you will send that data back to Earth so that it can be used by the right authorities and where it is required. And these are the main building blocks of this terminal. Now we can look at the fine pointing system a bit more here. Now, how to fit everything inside this? This is a simplified diagram of the telescope and the optical path here. Now, the red line is basically the laser signal coming in, and the blue line is the laser signal coming from the ground, and red one is the laser in space. Now, we've used something called as a dichroic mirror. Now, dichroic mirror, what it does is it separates different wavelengths. So it separates the 1545 and the 1590 that I talked to you about earlier, so that only the 1590 goes to the detector and not the one that is coming from our own laser inside the terminal. Then we have used a lens at the back which focuses the light onto the detector so that we can do our pointing and we can receive the signal strength is higher. As you can see, it's a concave lens, so it will converge the light. It's a convex lens, I'm sorry, it's a convex lens, so it will converge the light onto the beacon detector. Now, there is something called as a fine steering mirror, as you can see in the front. That's the first thing that comes to. And it also says that it has an optical range of plus minus 2 degrees. Now, what this fine steering mirror does? Fine steering mirror, it can do tip and tilt. It can move super fast. 1 kilohertz is the speed, so it can move 1,000 times, in a minute. And what it will do is, by doing that, it will make sure that the signal coming from the ground is sent to the right direction and aligns perfectly. It's we use this a bit in astronomy as well, but not as fast, as it is not required to be that fast, because you track the stars slowly according to the rotation of the earth. But here, as I said, the satellite is moving at 7.5 kilometers per second, and the importance of precision is very high. Otherwise, you will not be able to establish a link between the ground station and your satellite. Timing is of utmost importance. And this is what enables us to be able to do the right pointing and establish a signal. Many companies have tried, many science missions have been gone. Not everybody has been successful in establishing a link with a laser to the ground. It's not an easy thing to be able to do. And these are some technologies that enable a bit more. So I'll deep down into how we got to launch and what are some basic characteristics. As I mentioned, it's 10 centimeter by 10 centimeter by 10 centimeter. So you can see 96 mm. That's slightly smaller, and it's only a kilogram in mass. Now, here is something very important written, which is the material of the structure of the cube cap and the coefficient of thermal analysis. The coefficient of thermal analysis is basically, you need thermal expansion. You need this so that when you are in space, you can be minus 50 degrees suddenly, and then you can be, when you're facing the sun, you'll be suddenly plus 50, plus 60 degrees Celsius. Now, materials react to it differently. You need to be able, everything to be able to adapt to the environment it is in. And that's why you need a structure of the satellite which is very similar to the coefficient of thermal expansion of the CubeCat itself, of the laser terminal itself, be it any laser terminal, so that you can make sure that any expansion or contraction will keep things in place while it is going. So this is super important. Now, at the bottom, you can see qualified to NASA gas. Now, qualified to NASA gas is general environmental standards that are established, that are, specified by NASA. Basically, your vibration environment, your thermal environment, all of your radiation environment, all of these have certain limits, and there are certain rules that you have to adhere to survive a rocket launch and your satellite to be able to operate. And those things are laid out by NASA general environmental standards that have been provided. And these are different for different rockets. For an ISRO, so there will be standard for space, but some of the requirements will be different for different rockets. For an ISRO PSLV, it will be different. For a SpaceX Falcon 9, it'll be different. For an Ariane 5 or Ariane 6 from a European Space Agency, it'll be different. So these are all different rockets, and they all have a bit of difference in the environments that they take the satellites through. A little bit of basics about how we integrate this thing. So you need a clean room environment. You don't want any particles of dust or anything going inside this terminal into your optics. So you need a clean room environment to integrate this inside a satellite. It's very important that it is aligned to your satellite reference frame or your satellite. So basically, if you have the satellite and the terminal is at the front and your camera is at the back, or your camera is here and your terminal is here, and first you're looking at the earth through your camera, you're taking your images. Then you need to turn your satellite around so that you can point the laser for all the images you've taken to send it down to earth. So you turn your satellite. Now, it needs to make sure that the aperture of this terminal is aligned with the satellite. Otherwise, you will be shooting in the dark. You wouldn't know where your laser is pointing. So you need to know from it's very important to align. You've alignment in cars, for example, for your wheels, for your tires. Similar way we've alignment for the laser terminal. Okay, not maybe as simplified, but very similar alignment that you need to do so that you know where things are. Now, laser safety, as I mentioned, it's a 300 milliwatt laser. It's a class 3B laser, so we need some basic eyeglasses to make sure that everything is fine. Now, we do a lot of testing before we can move towards a launch. You need to be make sure you do a functional test. All the systems are working. So you see the laser turns on, the laser turns off. Your it's a mini computer in itself. It has its own brain. It has a processor in there. You give in information, it gives out information. So it's a mini thing, mini small computer there itself in it. So you need to make sure all the electronics are working. You have to put in a new software itself. Basically, the software that you would put in here, it's not going to be like Windows. This is something you've designed specifically to work with this. So in space is a very multidisciplinary field. We need specialist electronics people. We need specialist software, embedded systems engineer, people who can uh, complete a system. You need mechanical engineers, and then you need space and aerospace engineers to come at a system level. And that's how the system completes. So this is the importance of being multidisciplinary for space and specializing in a particular topic. For example, somebody who can design electronics using semiconductors is of high importance in the industry. Somebody who can do specialist software, somebody who knows the how to write the software for these chips. You're basically building a computer from scratch where you've been given the chips. You have to design the motherboard of the CPU. You have to write the software. There is no Windows, and you have to basically put that thing together and make sure everything works together. So you need specialist people who are able to do this. A bit about launch. What are the different things that we have to do before launch? Now, main is environmental testing. Now, third TVAC, that is the first one, thermal vacuum test. Now, you do this in launch sequence basically. Now, first thing when you are on a rocket and it starts to launch, first thing you're going to start feeling is vibration. Everything is going to shake, and you need to make sure that your system can survive launch. You have different requirements to be able to get through vibration. Then you have thermal vacuum. So after vibration and the temperature changes through the atmosphere, once your rocket reaches space, you are in vacuum of space. There is no atmosphere anymore. And the thermal environment is continuously changing. So you need to make sure everything survives in that. So a TVAC campaign is basically a big thermal vacuum chamber in which you can regulate temperatures, for example, from -50 to +50 degrees Celsius. and you also it can create a artificial vacuum inside that chamber so that we can see how things are performing on vacuum. Last but not the least, you see EMI and EMC. This is a bit more in detail. It's electromagnetic, uh, emissions. Basically, you want to see from your electronics, are they interfering with each other? Is there something that could cause problems? For example, you have other systems on the satellite, which could be cause problems due to your electronics, or somebody else's electronics can cause problem to your stuff. So you need to do this testing to ensure that your electronics are within their electromagnetic emissions are within a certain limit that has been set by different space agencies, by ISRO, by NASA, by ESA, for example. Here there are some numbers on what were the different vibration levels that we would need to have. These are all random vibration levels. Here is the situation. Like I was mentioning, we launched it. So it was on a satellite called the NorSat TD. This was a satellite built by the Norwegian Space Agency. It was a technical demonstration mission. It had 7 new technologies to be demonstrated from space. It was launched on out of those 7, one was our terminal small cat slash cube cat, as you can see here, and it was launched on Transporter 7 by a Falcon 9 by SpaceX in April of 2023. Here is some very basic satellite operations. I wouldn't dive into details here. It's super basic on how does this even happen. As I mentioned, the ground station fires the beam. Then the fine steering mirror is basically looking for the signal. It's looking for the laser beam from the ground. It is scanning. Once it's acquired and it gets logged on, the transmission stops. And basically, then you can transmit the mission data, and it lasts for as long as the ground station and satellite can see each other. This could be 5 minutes, this could be 1 minute, this could be 2 minutes. Clouds can be a problem with lasers. This is not a problem with radio, but clouds are a problem for lasers, especially for the wavelength that we have for communication. So 1545, it's not able to pierce through the clouds. It gets bounced off of clouds. So clouds are a challenge for for laser communications. But this is a what a basic operations would look like, how you would go about establishing a link with the ground station. Now we've talked mostly about the space terminal. Let's talk about what do we need on ground to be able to talk to this terminal and what kind of technologies are required. So this is the optical ground station that we connected with basically in The Hague. This is the first one that we connected with. And this is in the Netherlands, in Hague. And it is a massive observatory. So it's a big telescope, which has been modified to move very fast and have an optical bench and lasers to point to the satellite. And then once it receives the laser signal, it can send it to the optical bench for decoding of the signal. It's also a modem here. You have modem in your houses for modulating, demodulating. Similarly, we have a modem here. Looks very different than the modem that you have at house, but it takes the laser signal in, converts it into a digital signal that we can then use to get our information. Bit more of So you can ignore the text. That's a bit too much detail. I'll give you a bit of overview here. So basically, this is the inside of the ground station. What you need here. So you need a telescope. For this, you need a 60 centimeter, which is the diameter of the mirror of the telescope. Now you can see there is a fine steering mirror here as well to correct for errors. You have to control the telescope. It's moving. As I said, the satellite is going 7.5 kilometers per second. So it's going super fast. So the telescope has to move from here to here within 5 minutes, for example, or 10 minutes, for example. So it has to move really fast, and it needs to be stable while it's doing that. It has a transmitter, the laser transmitter, which it is sending to the satellite basically. and you have a receiver which gets the data and the digital converter. And for a link, basically for a link, for we made this calculation to see how much data we can get down. So for a northern European latitude, you're at a in an orbit of 550 kilometers, you can easily have 2 to 4 link opportunities, and you can have 15 orbits per day. Now in this, if you are transmitting at 1 gigabit per second, then you do for 5-minute link, you can downlink 300 gigabits of data in a pass. And in a day, if you have 4 links, you can easily get to 1.2 terabytes bits of data easily. And the timing accuracy is super important. So I'll skip the details here. You can ask me in the questions if you want to know this a bit more in detail. Moving on. Here are some more specs of the ground station and how the lasers were inside the ground station operating basically. So this was not a 60 centimeter, this was an 80 centimeter telescope. And as you can see, the wavelength is 1590, and the power for these were 6 watts per beam. And that's what was seen through the basically the terminal. And you can see we can do 1 gigabit per second because the size of the mirror here is quite big. Yeah, these are some basic information, but we can skip this. This is too much into details. Moving forward, to show you some in-orbit testing and results of what we got from our in-orbit demonstration, basically. So this is the first time we saw the light from the terminal onto our optical ground station. Now, I know you can't see everything, but what you can see is a point on the screen, but that's how we confirm that yes, this actually happened and this is actually working. So this was the first time that we were able to establish the link. I can share you some papers that are available, online that you can have a look at. And then here is a typical interface from a ground station perspective to basically see what are the different things that are being. So everything green here means all steps were done, and we could track the satellite. We could send the beacon up. The satellite saw the beacon. The satellite sent the laser down. We saw the laser as well, and then further data transfer was happening. And that's how we basically have the ground station interface on the ground to see everything is fine or not. I don't, this is a bit more detail. Don't know if this means anything to you guys, but this is an eye diagram. Eye diagram is what, confirms what is the data rate that you're operating at. Somebody who's doing RF or, lasers or data would be familiar with these things, but that basically shows us that we were able to transmit at 1 gigabit per second. And I think that's all from my side, and I'm happy to take questions if you have any. Thank you so much.
Thank you, Tushar. That was really nice, and amazing to know the kind of technology that has gone behind in bringing this laser satellite communication and everything. I'm pretty sure all our viewers have questions. I would ask you all to put it in the chat, the comment. We will pick it up. And to start off, Tushar, I have a question, right?
Please.
So I was just reading a little bit about it, and I saw that SpaceX Starlink is something which is already using laser satellite communication, and we know the number of satellites that are there. And I'm just I think you did talk a little bit about it, but I wanted to know a little more. For anything, there is some kind of interference that comes into picture. And when we're talking about this communication, and then there are so many satellites, we're not only talking about satellite just sending information for us here on Earth through to the ground station, but we're also talking about satellites talking to each other using the same technology. So let's say while two are communicating, and then there is a third one which is in between, because we're talking about so many satellites that are, let's say, not even part of this constellation, but then other satellites. So I just want to know a little bit in terms of the interference that happens with respect to this technology. Is there any kind of data that's getting disturbed, corrupted? I mean, what happens?
Sure, sure. No, definitely. That's a very good question. So, there is, as you mentioned, SpaceX and Starlink is already using it. And there's two kinds of ways you use this technology. Today, I talked mainly about direct to Earth, how you communicate from satellite to Earth. How Starlink is using is between satellites. So they are doing inter-satellite links. They are not communicating from satellite to Earth at the moment. No. So what happens with this interference? Basically, everybody has a different way of layering their information. We have inside there is encoding. So yes, there will be some sort of interference, but you can separate those two data basically. You would not you would not be actually needing to license it, but somebody can, yes. Now the thing is, it is so precise. You're basically shooting from such a distance into a very precise point. So if somebody doesn't know your location, you can't really do this. But if somebody is intentionally trying to do this, yes, there could be interference if they are able to get all those details about you, basically your wavelength as well. They know where you are. They know how you've packaged your information. Then if they manage to send the information exactly at the same time at the same place, then yes, you could have some interference that could be given, but that would be very intentional interference, and you would not have it in general. So for regular operations, this will not be the case. To track this, as I showed you for the ground station, you need very
Right,
specific technologies to be able to decode your data.
right.
So that's the bigger reason that it would not happen in general, but somebody could do it intentionally if they wanted to.
Right. I think that's there for everything. Coming to that, it brings me to another question. So you also spoke about the security purpose. Right now, also you mentioned about decoding and all of it, and we know there is another domain that is getting added, and like people are doing research. The countries are spending so much budget on that, which is quantum, and we have quantum communication. So can you tell me, um, if there's any handshakes between quantum and then optical? Is it the same thing we are talking about, or what's the difference? How is it kind of going together? Or I just want to know a little bit more about that.
Definitely. Definitely. No, no, that's an excellent question as well. So, quantum basically it starts with this. Optical communications are laying the basis for quantum communications. So you need optical first to have quantum. So they're not exactly the same thing, but you need one to do the other. You can't do quantum without optical. But the other way around is, if you, for example, from my CubeCAT, this laser terminal, I can't do quantum. I need more things. It is a one higher level of security and one more level of complexity in technology. So, how quantum would work is mainly what we're talking about is quantum key distribution. Now, this is a key that cannot be just easily decrypted by a normal computer. You need specific quantum computers, and they might be able to not do this as well. For this, on a satellite level, you need a single photon detection source basically. So you need to detect single photons of light to be able to do quantum and quantum key distribution. There is also a difference of wavelengths in this. So the current wavelength that this here is 1545 and 1590. I think quantum requires somewhere around 800 nanometers. So at the edge of the visible spectrum is what you require. So there are differences, but optical is the stepping stone to quantum. Optical will enable quantum basically, but you need more things to be added on to be able to do quantum communications.
Right. That's great to know. And I was actually listening to and seeing the pictures of what your company has been doing, and the last image which you showed us. This is the proof that we achieved. That was really nice. So I just want to know more in terms of, like, let's say, where all has this been being used by whom, and let's say, let's talk about what has been something that's already in use, like you spoke about RF and all of it, right? Now if you talk about like, let's say, laser communication, especially for satellites, what's the percentage of, I mean, if there is something that we can say, how many people are actually using and who are they, and um, what is it taking for them to um, be there to be very little, if it is very little?
For sure. Yeah, no, definitely. It's just the beginning actually. Not a lot of people are using laser satellite communication at the moment. Like this, our first launch was also a demonstrator to prove the technology in orbit that yes, it can survive launch. Yes, you can make links from space to Earth with lasers. So as you mentioned already, SpaceX is using it, for example, in their Starlinks. There are more companies coming up that will be using this. Currently we have a chicken and egg problem. For example, you know, so the ground for me right now, the competition would be radio itself. The ground infrastructure for radio exists. You have radio ground station. This is something we're using since the start of this of space, 1960s, 1970s, even before. So we have a way to receive data via radio, and it is globally located. Like we have stations everywhere around the world. This is not the case with optical ground stations at the moment. They are upcoming. So right now, the biggest question is, oh, where do I get my data down? And I'm like, okay, right now there's very limited places that you can get it, so you're not able to use all the advantages it offers at the moment. Secondly, clouds are a challenge. RF can peer through clouds, but infrared and lasers cannot. So there is work that needs to be done. So for example, especially for European countries here, they're so cloudy and so rainy all the time. The Netherlands, The Hague, probably the worst location to test this because it's cloudy all the time. We were very glad we were still able to make a link. It was clear that day. But basically, these are few challenges, and this is an up and coming technology. So right now, it's experimentation, it's proof of concept, and it's becoming commercial now. So it's starting now to become commercial. Where we have seen the use of this previously is NASA has used this since the moon landings. Like they have used lasers to confirm the distance. For example, they've communicated from the asteroid Psyche mission that they have sent the spacecraft. They communicate through lasers back to Earth, and that's the longest laser link they have established. So for long distance and deep space missions, lasers is something that's already in use there. For Mars missions, it will be in use. And for low Earth orbit missions, it'll be mostly to downlink vast amount of data. As you can see, we are in the data age. Everybody's on their phone, streaming through gigabytes of data a day, and we are going through. So this is the data age, and this is what will enable us to keep up with the data age, basically.
Great. I mean, in fact, two questions just came to my brain. I'm just seeing which one would be the right question to ask. Let me go with, I think, something that connects more is you were talking about the ground station. If you have used laser communication long back for the, very long distance, and now we are trying to use it here within the earth, and for between the satellites and all of it. I did see you mentioned about the change in the ground stations, because we cannot use the older ground station. And I also heard you saying it's about where will you get the data. So the question is, these ground stations that are there, which are built by everyone, and it is shared very nicely, I could say, between the countries, between the companies. um, all of this. So when these so these ground stations which we need especially for laser communication, how different would they be, and is there in terms of the engineering, in terms of technology, whatever is already there, at least the location wise, can it be still reused, repurposed with some small changes? Like, can you tell me a little bit in terms of the technology aspect with ground stations, especially for these laser communication or satellites? Yeah.
So the main difference between the two is for a radio ground station, you need a big dish that can receive the signals. And for an optical ground station, you need a telescope. And that's the most major difference that you have. And now the telescope needs to move quite quickly and needs to be quite precise. The dishes don't need to move that quickly. They can move slowly, slowly, slowly because the beam is in kilometers. So you don't need to have that much precise information, precise, pointing towards. So main difference is instead of dishes, we need telescopes. And as you would know, telescopes add complexity to everything. They need to be clean, need to be taken care of, and these are not so these are standard telescopes modified. So when you have a tracker for a telescope in an observatory, it's moving exact to the rotation of the earth, which is, we go 360 degrees in 24 hours, so 15 degrees an hour. So you're moving only a degree every 4 minutes. Here you're crossing through the sky in 5 minutes. So that's the change that's required. Then the laser light that you get, the beam, you need to focus it on the detector. Then you need to transfer that signal to a digital converter, basically. And then that converts the signal to finally digital signals that are useful for us. And then you need a laser inside that's pointing towards the satellite. So these are the things that are the added complexity to this. So they are a bit more, they're a bit more complex to make work. And there is no, you could modify previous observatories. For example, there are old observatories that are not being used anymore, for example. And those are some things that could be really repurposed to do this.
Right. So basically, we have to go back in time and see what all observatories that were there. For sure, they would be geographically set up in a nice place for astronomy, but now we would use it for space tech, and all of
This is
it. That's
already
good.
happening. There are a few who have already done this and are doing this as we speak. Like there are a few observatories that were converted to become ground stations, and now they can serve dual purpose. They can also do astronomy. They can also serve as an optical ground station.
Again, the data sharing could still happen between the countries and the companies, which is enabled through your decoding process, if I'm not wrong.
Yeah, it works differently with governments. It's different right now. Everybody wants to have their own. They don't want to share as well.
Yes.
So this is a recurring thing in the world at the moment, which is not the best thing, but well, it is it is how it is progressing at the moment.
Right, right. So we do have one question that has come up, and I also heard you actually telling about it. Um, so the clouds or the turbulence, the weather, all of it. There is some level of interference that again causes. So like you yourself mentioned, weather wouldn't affect the RF, but here it does. So is it going to be a big challenge for us to make this technology bigger and usable, or what exactly has to be done in this domain?
Oh, definitely. It is a bit of a challenge here in terms of availability. For example, it depends on the mission. If you need immediate data, for example, there is disaster management. There's a natural disaster somewhere, and you need to transfer that data right away. And oh, there are clouds, I can't transmit that data. That's not an excuse you can use at that time. So you need to be equipped with both at that time and make sure you use the best out of both at the time. There are technologies being looked at. There are lasers that can pierce through clouds. So if you go into the 2.1 nanometer range, those can get through clouds, through mist, through everything. There could be also, if you have more ground stations than RF ground stations, so there has to be a factor of 10 somewhere. Either they become 10 times less expensive and they're 10 times more available, then you can beat this. Then you can quickly transfer the data somewhere and get it across. So then you can beat this. But yeah, there needs to be work done there. There is could you could change the technology a bit itself. You could have more ground stations. So these are different ways of combating this.
Right, right. Probably a last question to you, Tushar, which is for sure not about what we discussed so far. Um, ISU, and you have earlier been in the space communication domain, and we are in the space education domain. So we mostly, everyone would want to keep learning something, do something new. So for all those students who are interested about space, passionate about space, who would like to do something new and different, I want you to share what is that you learned, what is that you have experienced, what is that you're feeling being out there, and what do you feel about the opportunities, and what do you feel that one must do over here in India, or whoever is watching, or be it anywhere. uh, what is that they must, what are the actions that they must take, uh, very generally, but to which will help them to make them achieve their goals, Tushar.
Definitely. I'll try to speak a bit. I don't know if I can summarize it. For I can talk a bit about my experience and try to
Yes.
share something. So
Yes.
for me, like since I was a kid, I've had a huge interest in planes, and then I grew up during the space shuttle era. So I saw Kalpana Chawla, Sunita Williams, and that plane became a space plane very quickly. And then it was like, okay, I have to do space. One thing is keep your passion alive, no matter what everybody says. Right now you go into the class and you ask third graders how many of you want to be astronaut. Everybody would raise their hand, and then you go to 12th standard and that will change, and some of their curiosity dies in the middle. So that is the thing. And the thing is keep asking questions. No question is stupid. Ask as many questions as you can. Be curious. And don't limit yourselves to form of learnings. Basically right now we're, as I said, we're in the data age. There is so many ways you can learn about something. If you're interested about something, type it in Google, type it on YouTube, and go. Definitely check your sources. There is a lot of false information, so please, make sure you wherever you are looking at this information, it's correct and it's right. But if you have a question, don't don't push it away. Just look at it. Look at the question. I think that's the most important thing I would say is never let your passion die. And if you have a passion for space, one thing good about space is that you can enter space in 1,000 different ways. You can be a chemical engineer and make rocket fuel. You can be a software engineer and design software for a satellite. You can be an electronics engineer, embedded systems engineer. You could, but make sure to always, okay, go specialize in your computer science, go specialize in electronics, have an aspect of space somehow. You have to, and now that is something you have to do by yourself, and the whole world will come and tell you do not do it, or it wouldn't happen, or something like this. And I've been through the same, and tell you, don't stop. It pays off. You'll get to do your thing if you just keep at it. So if you have passion for space, never stop asking questions in that sense, and don't bury your question. Like even if it is a stupid question, you want to know the answers to those questions. And yeah, that's all I can say. Is never stop asking questions. I think that's the important one. And if you had a passion about space, don't forget about it. It's not impossible to do something in space. If me, Nikita can do it, anybody can do it. Basically, it's the same.
Thanks a lot, Tushar, for sharing your knowledge, your experience, and everything that you have gained through your journey among all the audience that we have today on this show, and among all those who are going to watch this video for whenever they would want. Thanks a lot for your time, Tushar, and I wish you all the best. I wish you get great deals for your company, and I also wish this laser satellite technology becomes something bigger, and people
Definitely.
come up with solutions for all the challenges we discussed as well. Thanks a lot, Tusha, for joining, and for all those who joined again. Thanks a lot. We will come back again with another amazing space talk on another amazing topic. Until then, stay tuned. Keep watching all other videos that we already have. Thank you very much, and bye bye.
Thank you.